Hello everyone, sorry I couldn't make it yesterday. So today I'm going to talk about seeing the dark universe through the lens of weak lensing, and in particular cosmic shear. Let's see, what is cosmic shear? So this cartoon here kind of shows how cosmic shear works. You have galaxies in the background and the light passes by massive structures, so this could be your large-scale structures. And as a result of the gravity of these structures, the path of light is bent, and then the images you see are distorted. Now, if you have two such galaxies in the background and their light passes by similar structures, it will be similarly distorted, creating a correlation between the shapes of their images. And this correlation is what we measure as the main signal for cosmic shear. What it depends on is whatever structure is in the middle, so between us and these sources. And the way we can model the signal is through having some cosmology that can tell us what the structure formation is, and also knowing how far away these galaxies are. So we need the distance to these galaxies as well. And for that, we generally use redshift as a proxy for distance. Okay, so that was like a very simple way of explaining what cosmic shear is, but let's go a little bit into detail of how it actually works in practice. All right, so in practice, you can't just take two galaxies and measure the signal, because the signal is very weak. It should actually be called very, very weak lensing. So what you need is tens of millions of galaxies to be able to get a meaningful signal. And that's why we need high-resolution, deep images. We also take the images in multiple photometric bands, so we can get the colors of the objects. And once we have these colors, we can divide the objects into galaxies and stars using the colors and make our catalogs. Then from our catalogs, we measure the shapes of the galaxies, which is one of the main ingredients we need. And we measure the redshifts of the galaxies using their colors that we got. So this is an estimate of the redshifts. Now, because our information is limited about both the shapes and the redshifts, what we get out is can be biased. And we need to calibrate both of these components. And I'll talk about that a little bit in a few slides. Now that we have our galaxy shapes and galaxy redshifts, we first divide the galaxies into redshift bins, so they're called tomographic bins normally. So we can get the evolution of matter, so a bit more information from the data. And then we correlate the shapes of galaxies to get the signal. Okay, so we have the signal. Now we need the model to compare it with. So first of all, you have to choose your cosmological model. Normally, it's the standard Flatland-CDM, but you can choose something else if you want. But the cosmological model doesn't directly tell you what the structures are, so you need to be able to solve the nonlinear evolution to get the structure formation. And for that, you can use simulations, for example, or use analytical models such as the halo model to get an estimate for how the structures form. In particular, because we're looking at two-point statistics, we need the power spectra, so we need the matter power spectrum. So once you have this, then you can transform your power spectrum through some integrals to something that looks like your observable. And then also model the error on the observable, so your covariance matrix. But before you can compare your model signal to your actual signal, you need to think about some nuisance effects, which are increasingly becoming not just nuisance, becoming more important than that. So nuisance effects could be anything that, say, is not modeled in the calibration. For example, maybe when you're calibrating the data, you have some uncertainty. Or it could be things that are not in your cosmological model, but still affect the signal, for example, astrophysical effects. The two main astrophysical effects that are important here are effects of baryon feedback which you won't get if you only assume dark matter or in your simulations or in model. And that can move matter in galaxy halos. And then the other one is the fact that galaxies could be intrinsically aligned because of where they form. So if two galaxies are near the same dark matter halo, they will have an alignment because of that. Okay, so once you have accounted for all your nuisance effects, now it's time to compare your actual signal with your model signal through a likelihood analysis. And then finally do your inference. So that's getting the numbers that you need. Okay, so this picture is not complete without this last ingredient, that is blinding. So that's very important as well. Because there are so many steps in between all of these steps as well, and there are choices to be made. And given that we have some preconceived ideas of what the result should be, it's very easy to have confirmation bias. So we need to blind the analysis before we get to this step. And a lot of the weak lensing surveys are now taking some form of blinding strategy for the analysis. And if you are doing any data analysis, I really recommend to you that do the same. So it's a thing that I always talk about. All right. Okay, so I promised I would talk a little bit about calibration. So first of all, let me tell you how the shape measurement works. So if you have a galaxy and it actually looks like this, I don't know if you can see it, but this is actually a very big galaxy. Normal our galaxies are much smaller than this. Then you have gravitational lensing that shears it, and it shears it even less than this. But then you have atmospheric effects or your telescope that causes blaring. And then on top of that, you have your detector that pixelizes it. And then on top of that, you have noise. So from this image that you got, you want to know what this one is. So how do we do that? So what we do is we find the stars. Remember, we use the colors to identify which ones are stars. And we know that they should be point sources. So there's no gravitational lensing happening on them, but all the other effects are there. So if we can find out what was the effect that made this point into this thing here and reverse it, then we can do the same to the galaxies. So that's the point spread function effect plus detector effect plus all the effects. Now this needs calibration because of a few different reasons. One is that the noise can cause some uncertainty in the shapes. And another effect is that you can have blending. So you can have galaxies that are close to each other, so they're blended. And with this kind of method, you won't catch them. So you need to have simulations that are realistic. So they're called image simulations usually. Okay? And here, for example, in this paper, they looked at what happens if you have blended objects. Aside from the shapes, potential bias in the shape measurement, you can also bias the redshift measurement. So you can bias both of your main ingredients. So here you have two galaxies, they're separated obviously, and you know that where the redshift is. And now if you have these galaxies and they are overlapping, then you might get redshifts for them that are not correct. Okay, so now let's look at the other ingredients. That's the redshifts of galaxies and how do we calibrate them. So this is an example from KIDS. KIDS has 4 bands UGRI in optical, and they're shown here. Now imagine you have a galaxy. This is at redshift 0, and this is the spectral density of the galaxy. And you can see there is a prominent break around here, so that's up in U band currently. Now, if you move this galaxy to redshift 0.9, this break moves to band I, and you can imagine if I push it to higher redshifts, it's going to go out of this. So, What happens with kids is that we have this sister survey called Viking, which adds 5 extra bands, which means that if a galaxy goes to higher redshifts, we can still detect it through these extra bands that are in near infrared. Okay, so now if I move it to 1.2, you can see that the break has moved to Z. And it also helps with degeneracies between spectral densities. Okay, now that again, because we have a limited number of bands, you still might get some errors that you need to calibrate. So what normally people do is use some spectroscopic sample for which you know the redshift, but it's a subsample of your full sample that you have photometric redshifts for. And you use the spectroscopic redshifts to calibrate your photometric redshift. For example, here 2 methods have been used. One is called self-organizing maps. And basically what you do is you group the galaxies based on their colors and properties that you have from the data into cells, and then you try to match these cells between the spectroscopic sample and the photometric sample, and then assign the same redshift to both samples. And then another method, so that's shown in red under the blue line. And then another method is using cross correlations with spectroscopic samples. So here you're not using the colors anymore, but you're using the fact that the galaxies are near each other, they will be clustered, while if they're not actually physically near each other, they won't be clustered. And these, the measurement is shown in black. So you get these redshift distributions. So these are 5 tomographic bins. And then for kids, for example, what we did was to look at the black data points and then compare them with the red ones and see how much the red curve has to shift so that the black, so it matches the black. So it gets the best match with black. And that's shown in blue, and as you can see, blue is almost on top of red, aside from maybe this case where you can see they're not exactly on top of each other, and this shows that the 2 methods are consistent. Okay, now I told you about how weak lensing works and what we need to do to the data. Now let me give you a little bit of a history about tension, given that this is a conference about tension. Okay, so it all started in 2013 for weak lensing. So this is a plot from this conference. That was in 2013, I think, or maybe it was 14. And this is showing this banana here. It's showing the cosmic banana. And sigma 8 had the antilope clustering, and then we have omega m matter density, and this is the constraints that you get from CFHD lens, which was one of the first weak lensing surveys that actually could set constraints on parameters. And this is like a thing that you always see from any cosmic shear analysis, this kind of banana, because we always have this kind of degeneracy, and that's why we normally look at this direction, which is called S8. And that's a combination of sigma 8 and omega m, rather than looking at sigma 8 and omega m separately. Okay, so when this paper came out, the Planck results hadn't been out yet, so it was WMAP, and WMAP matched with this very well, and they combined it, and we got this blue here. Then the Planck results came out, and it was here. And this was the start of the tension for S8. So this is like, I don't know, 2.5 or something like that, sigma. So this is where we were at the start. Now let's see what happened since then. Okay, so I'm going to only focus on the current weak lensing survey, the ongoing ones. And here this is showing the sky map, so the map of each of them. So there are 3 of them. There is the Des tree as shown in green, and it's the biggest one in terms of area. And then we have HSC, so high versus prime count, which is the purple ones, and it's in different parts of the sky. And that one is the smaller one in terms of area, but it's the deepest one. So it has the highest number density of galaxies. And then we have KIDS in orange. And KIDS has medium-sized area and medium-sized depth, but its specialty is that it has more photometric bands for estimating the redshift. Okay, so they're all complementary, and you can see that there's some overlap between them too. All right, so first of all, let me show you some of the measurements, what we actually observe. For example, here you can see the 2-point correlation functions of shear. So that's one of the plots that you would normally see in a cosmic shear paper. And you can see there are rows of panels here. Each panel is showing the correlation between 2 tomographic bins, and we show all the unique correlations normally. And then you have the data and then the best fit on top of it. Okay. You can also go to free space and measure power spectra, such as here for HSC. Or you can use other statistics, for example, Casabi's, which is a kind of compression of the 2-point correlation functions. And it has some good properties that are important for cosmic shear. For example, you can separate the E modes, which are the actual signal that we want to measure, from B modes, which in this case are normally from systematics. Okay, so I'm not going to go through all the things that are happening here because there's a lot. But I want to just show that generally you see this kind of plots in recleansing and other survey analysis, and what it's trying to show is that this is your main parameter, and what happens if you change certain parts of your analysis. And normally what you get is that the points move, but they don't move very much. And this is trying to show that the analysis is robust. So that's for KIDS 1000, then we have for this year 3, and then we also have it for Hypersuprime Cam year 3, which came out very recently. Okay? All right, so one important thing here is how do we, when we measure things from different 2-point statistics, are they actually consistent with each other? Because the reason we measure from different 2-point statistics is because they are sensitive to different parts of the data, so they have different scale dependence. If we show that they're consistent with each other, that's showing that the different scales, the way we model them and the way we clean them, is making them consistent. So here, this plot is showing mock results. So if you have 100 noisy microrealizations of the data, and you analyze it with 3 different 2-point statistics, you expect to get this kind of differences between them. So each of them, for example, this orange one is showing the difference between Casabi's and 2-point correlation functions. And if I summarize this in one sentence, it is you expect to get 0.8 sigma differences between different 2-point statistics 68% of times that you do your analysis. So if you see, I don't know, 2 HSC papers, and one of them is giving you one result, and one giving you another result, and they're using different 2-point statistics, if it is like within 1 sigma or so, it's not surprising. You can easily get this kind of differences because of just neural noise realization. And in fact, in HSC year 1, they also looked at the consistency between the different 2-point statistics. And you can see that they move along the degeneracy, but they're all roughly on top of each other. Okay. How much time do I have?
Still almost 20 minutes.
So I have 20 minutes left. Oh?
80.
Right, okay. Alright, so I told you about these 3 surveys, but what if we combine the results of these 3 surveys? And this was done in a relatively recent paper by the Rubin LSST team. So they looked at the combining Kids 1000, HSC year 1, and this year 1 data. And you can see the maps here. So if you remember, the DES map that I showed you was much bigger than this. It looks like a tank here. But this is year 1, so it doesn't have all of it. And they can see there's some overlap still between HSC and kids, so they had to think of how to deal with that. So what they do is they don't touch anything to do with the calibration of the data, so how the redshifts are measured and how the shapes are measured, but they try to harmonize the analysis choices. So they use two-point correlation functions as their statistics for all of them. And they unify the angular scale cuts, so use the same scale cuts, and then they unify the modeling choices. So what kind of nonlinear power do you use, what do you do for your intrinsic alignments, what do you do for your variant feedback. And you can see here, this is showing the public results, so this is as each survey has published. And then these two panels are showing their two reanalysis. So one of them is showing a more conservative scale cut. This is to remove the effect of baryon feedback. And then this one's showing less conservative scale cut by using a method that can marginalize over baryon feedback. That's called HM code. And you can see that the results from the public analysis change when they do this. So both they move a little bit and the sizes of the errors as well. So this was a very important result because it shows that the analysis choices matter. So you can shift things when you do analysis you choose different analysis choices. Although it shouldn't have come as a big surprise, because if you remember, I'm showing you these plots here. And that's what these plots are showing as well. That if you change your analysis choices, you can move things around, you can have different error bars. But generally, because these are normally like these huge plots, maybe their impact is not as appreciated. So once you put them together and really carefully analyze them, this is when you realize how important it is. Okay? And then they moved on to combining these. And I'm showing one of their results for combining, how they managed to do that. So this one is from the less conservative cuts, so having smaller error bars. And here you can see two different results, and that one is if you remove HSC from where kids and HSC have overlap, and the other one is if you remove kids from where they have overlap. So these are the purple and the gray ones here, and then the plant results are shown here as well. And we're looking here at S8 and omega m. So S8, if you remember, is a combination of sigma 8 and omega m. That's along the width of the banana. So the main result was how the error on S8 changes, and they get so HSC error they have is 0.02, and then kids is 0.02, and then this is 0.24, and once they combine it, they get an error that is 0.012. So it's quite a lot smaller, and then if you compare that with the plant fiducial error, it's smaller than that. So it's showing that if you combine these together, you can get an error which is pretty small. All right. Okay, so finally, I want to talk about this new result. So if I gave you the talk yesterday, it would have been more impactful because the paper had just come out. So, but unfortunately, I couldn't make it yesterday. So basically, what we done, this started at the same time. So we were doing this at the same time as the previous analysis I showed you. what's happening. But here we're focusing on the third year dark energy survey results, so there's year 3, and combining it with KIDS 1000 data. Towards the end of the analysis, the HSC year 3 data also came out, and we contacted them and asked if they would join the analysis. So they did the reanalysis using our method as well, but we didn't combine them at the end. So here, these pictures you're seeing are the people who led the analysis. So the paper is a DES and KIDS collaboration at all, because we're using the same data that loads of people have been working on for many years. But the analysis is done by these six people mainly. And you can see who's in DES and who's in KIDS, and Alex and Ami are also officially in KIDS, although they haven't been really active in KIDS recently. Okay, so how long do I have? 12. Okay, good. So what we did was kind of similar to what the LSST analysis that I showed you earlier. We didn't touch this part. So we didn't touch anything to do with catalogs, galaxy shapes, galaxy redshifts, calibration, and so on. What we changed was in this region, that's pink. So how do you do your nonlinear analysis? How do you deal with your nuisance effects? How do you do your likelihood analysis and inference? And then the signal, I have also drawn a circle around it because some aspects of it changed, but not all of it. So we kept the same 2-point statistics that each of the surveys chose. So 2-point correlation functions for the year 3 and series for KIDS 1000. And then we had to remeasure the signal for DES because here, as you can see, there's a bit of overlap between them. So what we did was we removed this part of DES and kept the KIDS data because it doesn't affect their data that much. So the signal had to be remeasured. Okay, so and then we also asked the HSC team to do the reanalysis. So what in the top panel, we can see their original analysis, so using their two-point correlation functions and the power spectrum. And then in the bottom, what you can see is the analysis once they follow our hybrid choices. So I should probably tell you what the hybrid choices were before that. Let's go back here. So I haven't really gone into detail of how you actually model the things. So here, for example, when you're using your model to do nonlinear modeling, people usually use something like HaloFit, which was fitted to simulations, or HM code, which you mentioned earlier, which is an augmented Halo model with some parameters that are fitted to simulations. Or they might use an emulator. Now, these all give you very similar results, but they have percent level differences that can add up to being something large. So we had to, basically what we did was we compared these methods, these codes with the newest simulations, so the Euclid emulator 2, and found the one that has the closest match. So that was our choice for here. And then for the nuisance effects, we had to, for some of the effects like intrinsic alignments, we don't really know what is the best model. So we chose 2 things, but our main analysis is using something that's in between what KIDS and DES chose. And then for our likelihood analysis, it was the choice of samplers, and we chose the sampler that gave us the most reliable result. Okay, so these are the things we changed. Now, and here you can see what happens with to the KIDS data and to the DES data when we do that. I'm not showing you the previous result here, but in another plot you'll see that. You can see that if you remember where they were before, they are both shifted high. So the S8 value is shifted high. Now for HSC, you can see when we do the reanalysis using our hybrid setup, nothing much happens. And this is because the choices they made canceled each other. But while the choices kids and Des made went in the same direction. So then once you move to the hybrid analysis, it shifted both of them a little bit higher. Okay, so this is part of that plot that you saw earlier. So this is our hybrid analysis result. And you have, for comparison, the Planck result here. And all of these analyses are using the hybrid choice. So you can see they're still all consistent with each other. And they're all below the Planck result. But they're no longer the 3 sigma or so that we saw before, so it's like a less tension. So the tension between this pink one and the blue one here is 1.7 sigma or so. So you could say it's not a tension anymore. Okay, so what happens if we look at some of our analysis choices? And I've chosen a few that are maybe more interesting here. First one is what we chose for our fiduciary analysis is to assume that the sum of the masses of neutrinos is not constant. But what happens if you fix that to the minimum value? You can see that the result shifts a little bit up, but this we found that is mainly an effect of projection effects in our posteriors. So if you look at the full posterior, actually these two match with each other. But the other two that are more interesting are these two. So this is looking at choices of intrinsic alignments. And as I mentioned, intrinsic alignments is something we don't really know exactly how it works. And the hybrid choice is using something that is a simple model. It's called NLA, it's a nonlinear alignment model. But it's allowing it to have a redshift dependence. But this one at the bottom is a model that has more flexibility. It allows for some scale dependence and so on. And this is the model that Des had used. It's called tidal alignment tidal torquing. So when you use the NLA without any redshift dependence, that's what kids have used, you don't get any difference between the results. So it's this point here. But once you shift to TAT, which is the more complex model, you shift the results downward by about a sigma. And this was, I think, the most interesting result from the analysis, aside from the fact that we need to work together and whenever you combine data, you need to revisit your analysis choices because your errors are going to shrink. Something that was maybe 0.5 sigma and okay before, now might not be. This is the most interesting thing, I think. So if we now look at the tension for this point versus Planck, it's more than 2 sigma. So we're going back to where we were at the start with efficiency, if you believe this point. If you believe this point, then it's not a tension anymore. Okay. Alright, so here I've selected a number of cosmic shear results. So in the top you can see the Des results. So the first one, SV, is the first result, and then you have year 3, year 1, and year 3. So these are like all the main analysis of the recleansing. So I'm including any reanalysis here. Then you have HSC year 1 and year 3 in purple here. You can see that it hasn't really moved. And then you have the kids results, kids 450, KB 450, and kids 1000 in orange. And then finally, the combined analysis that we've done recently in pink. And then for comparison, we have the Planck fiduciary results. So what does this mean? Is the tension solved, or is it still there? So,
I think if you basically restrict the models in Planck, right, to W max, you will resolve this. That's what I got from your W max talk. It was very nice.
yeah, W map doesn't have any tension.
Right, so if we put W map in there, it'd probably just be perfect, right?
Yeah.
Just cut the multiples.
Yeah. So not a time finder.
No, I'm just saying that there's evolution in Planck between low and high multiples.
Yeah.
And it solves your problem, right?
Yeah, it does, definitely.
It's well expressed.
Yeah, so, but the thing is, if you do believe Planck, let's say, and the high multiples as well, we still have the same trend as before. Even though the amount of tension has reduced, we're still all on one side of it. And at the end of the day, if you think about the scales and redshift we're sensitive to, maybe it's not such a surprise that we're seeing this kind of differences. And it's quite likely there's something in the universe we missed and didn't model, especially in the nonlinear scale. Okay, I'll just summarize here. So cosmic shear analysis results, even though we have moved around as we change our analysis choices, are consistent, still consistent. And we still find lower values of S8, although the tension maybe is not there or is lower. Then I want to stress again that we need to have our analysis blinded more now than ever, because we're all interested in this question. And then when you want to combine survey results, don't just take the numbers and add them together, because there are things under the hood that don't match. And once you start matching them, you get a different result, as you've seen with these two papers that I talked about. And then if you want to look at alternative models, you need to make sure you can model the nonlinear effects and any nuisance effects that might change, like intrinsic alignments and variant feedback. And finally, if you want to know more about the Des Kids paper, obviously you can read the paper, it's on archive, or you can go to Cosmology Talks YouTube page where we talk about it in more detail. Thank you very much.
Can I just have one bin and throw away four?
Sorry, I didn't get the last one.
What does it? You have 5 tomographic bins or 4 tomographic bins, depending on the survey. You know, why can't I just do the analysis bin by bin by bin?
So they're asking about tomographic bins and why we use multiple tomographic bins and why we combine them. So if you use one tomographic bin, basically you're combining all the structures in the middle together.
I want to take 3 of them away and just use that low redshift one. Then I want to use medium redshift, medium, you know, and then high redshift. That's what I want to do.
So what you miss then is the cross correlations between them, if you do that. And that actually gives you quite a high signal. If I show you the plot again. I don't know what, any of them. So you can see, okay, so this is bin 5 with itself. And you can see the signal's high. Also, bin 4 and 5 together give you a high signal. Higher than just 4 itself. And so on. So what you want to do is just look at the diagonals.
Right.
And you just miss everything that's here.
Right. And so you would check for a shift in your SA values by using tomographic bins, right? It's feasible analysis. It can be done. The errors may be large.
Yeah.
But if there is a trend, you'll find it.
Yeah.
It's something you should do.
So the thing is, I think it's an interesting thing to look at. The problem is currently, because this is the closest thing I can show you to that. So these last points, what we're doing is removing each of the redshift bins and reanalyzing. And if you remove 1, 2, and 3, nothing happens to the data. That's because
correlations, right?
and this is because these 3 don't have that much signal. So it's only 4 and 5, and you get this kind of shift. So that's the problem, that we can't get very much out of it currently, but maybe if you combine kids, HSC and DES, you can do that.
in one of the models of intrinsic alignment, CATT, yes, so SA becomes much smaller. So can you give us a intuitive description what's happening in this model? Why there is less alignment somehow?
Don't have a thought for it, but I'll just go back to the. Oh no, this way. Go back to the result just so everyone knows what we're talking about. So basically they're asking about the tidal alignment, tidal torquing model and why you get a smaller value here. And so the difference between NLA and TAT is that NLA you have, you assume that the shape of the signal is constant and that comes from your microphone spectrum. And then you have this amplitude that you're allowed to change, and you have just this one parameter. With TAT, you have 5 parameters. 2 of them are redshift dependent, so you could say you have 3 parameters. And with these 3 parameters, you allow for the shape of the signal to change as well. So it could be that what TAT, this one, is seeing is not necessarily that TAT is correct. It's more that maybe there is something in the nonlinear region that's not picked up by our modeling. It could be in the power spectrum, it could be in the intrinsic alignment, or it could be somewhere else, like in back and feedback. And when we use this model to fit the data, it's finding that thing. Or it could be just a noise realization, which is boring.
Question, I see that EF is asymmetric. For TATT. So the diagram, this is the mean or the maximum?
So these are all mean.
Mean, okay.
Yes.
And the maximum is?
Maximum is actually, so if you look at the maximum of the full posterior,
Yes, right.
it's actually below.
Below.
Yeah. So actually we looked at that because we thought maybe this is a projection effect, but if you look at the projection effect, it makes it even worse. So you get like 1.3 sigma effect. Yeah.
Next question.
The question is, James Webb Telescope showed some stronger growth at early times, while these results, of course, this tension shows a weaker growth. Would one talk about the tension between this data and the James Webb data?
Which data set?
This constraint that we have here, the James Webb Space Telescope.
Oh, yeah. I'm not quite sure if there is much relation there. I don't know, do you have any ideas about that?
The basic idea that you have early galaxies forming, and this means that you have stronger growth at early times, while these results show weaker growth at late times. So I can basically, in the context of standard model, try to compare this and show some additional attention to the one that you have shown here.
Yeah, that's good idea. I haven't really looked at the results in detail to know how they will compare with ours. The thing is, our S8 has moved up. So
Yeah, Anders, we wrote that paper. SA involves a redshift in RSD data. It's been written. Someone might referee though, not you.
So maybe another questions.
From the mirror.
If not,
Okay. A very deep question. But is it still the best place where you look at 8 megapass? 1 megapass.
it's historic. It's historic, and you know, like where it comes from, because like if you assume, I don't know, if I said let's say at 8 we're going to say it's 1 and so on. So that's where it comes from, right? Thing is, you could probably what you could do is we know you look at S8, right? And S8 is basically this thing here. And you could try to look at the full posterior and find the combination of parameters that has the tightest error bar. And it will probably be something close to S8. It might not be exactly S8, and that's all we care about.
So you check.
Yes, you could try to come up with some other parameter that's even tighter.
yes.
If I can react to this, the only, not counter-argument, the thing that I would like to push back on is the scales associated to sigma 8 doesn't really seem to, even though when you do the lambda CDM fit, then you do the projection because it just, you can extrapolate and and look at sigma and scale it, but compared to what you're actually measuring, it's a bit confusing in a sense, because you are converting anything into sigma, but really where the power suppression would occur is potentially at much smaller scales. So what I said earlier, for instance, was a little bit naive when I was showing the sigma kernel and saying, oh, the sigma scale. Because really what we need to do if we want to address whatever is left of the tension, it's not a fluke, blah, 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 is maybe on smaller scales, given the fact that the weak lensing data will really have overlap on smaller scales.
Yeah.
Maybe there is anyway, maybe it's sigma 15, I don't know, 12, whatever. The point is maybe there is a scale that you could associate that would be just simpler for theorists like me to try.
Yeah, well, the thing is, we do have some plots of power spectrum that in our papers, usually the methodology papers, where you can see how the scales vary and like which scales you're actually sensitive to. So, I don't know, we are probably sensitive to scales between K of 0.1 or so to maximum 10, probably peaking around 1 or so.
Because what I have in mind, for instance, is if it's, for instance, fully baryon, if it's a fully statistical fluke, forget what I'm saying, but if it's fully baryons, like it's been suggested, for instance, on paper, baryons, if you look at it, they should not really affect sigma 8 in a sense, but they definitely affect the rest of the frequency constraints, for sure, which then, because it's projecting back into the sigma 8. That's why it's a bit confusing.
Yeah, exactly. So the thing is, we show sigma 8 all the time because that's a parameter people know. It's not so much, but the thing is, there is degeneracies with other effects. So you change something, it will affect sigma 8. Although sigma 8 shouldn't change, it's just because there is this degeneracy that you get this result.
Just this is also a problem in media. Sigma 8. Right? This is also a media problem, right?
Yeah, it's a combination of the two. Yeah.
So, if I may propose to continue the discussion of the topic 20, and together here at 11:10, and now thank you, Marika.